In the previous section, we compiled an FPGA VI and described an overview of the compilation process. By the end of this module, you will be able to describe the various stages of the compilation process. Okay, let's talk about the different stages of the compilation process. First, we'll start with generate intermediate files. Here's where LabVIEW will convert the FPGA VI into intermediate files such as HDL code and send it to the compile server. The next step is queuing. Here's where the compile server will queue the jobs and send the intermediate files to the compile worker for compiling. The next step is HDL compilation, analysis, and synthesis. This is where the compile worker transforms intermediate files, such as VHDL code, into digital logic elements. The next step is mapping. During mapping, the compile worker divides the application logic between the physical building blocks on the FPGA. Next, we have placing and routing. The compile worker assigns the logic to physical building blocks on the FPGA and routes the connections between the logic blocks to meet the space or timing constraints of the compilation. After that, then we'll get to generating the bit stream, and this is where the compile worker creates binary data that LabVIEW saves inside a bit file. And then lastly, we've got the bit file creation. And this is where LabVIEW saves the bit file in a subdirectory of the project directory, and from there you can either download or run that application on the FPGA. Okay, so when you're compiling your FPGA VI and you have your FPGA VI up and you click run, the first thing that's going to happen is it's going to start generating intermediate files. So this window will launch, and in the meantime it'll take that FPGA VI and start generating the HDL code for it. So one thing to remember is once your compilation starts, do not edit your FPGA VI. Okay? Once you've created your FPGA VI and start compiling it, it's compiling it for that instance of the FPGA VI. So you want to make sure that the compilation finishes and you test it. If you were to start compiling your FPGA VI and then in the middle of the compilation you go back to the FPGA VI and start changing it and saving it, then that compilation no longer is associated with your new instance of your FPGA VI. So the takeaway here is once you start compiling your FPGA VI, don't make any changes to it until you've finished testing the actual compiled FPGA code. The last bullet here says you can create a compilation queue by starting another compilation while the first one is still running. So if I was to open up an FPGA VI and then hit run, and then my compile worker is already working on that first FPGA VI, I could take another FPGA VI and hit run, and what that would do is it would queue up the compilation. And you could queue up several different VIs, and then the compile worker and server will handle queuing those up and will handle the order of compiling those VIs and sending the information back. So after LabVIEW is done generating those intermediate files, it will pop up the compilation status window. So from this window, you're going to be able to look at different reports. So to look at a specific report, you would just go to the reports item in this window and select the report that you want to look at. So as the FPGA VI is compiling, you'll have more and more reports available as the time passes by. You also have the option to close this window, so you can either just close the window and have it still be updated with the compilation status. You can also disconnect this window from the compilation status, even though the compilation is still happening. Or you can also have the option to cancel all compilations as well. So if you were to cancel the compilation, it would tell the compilation worker to stop compiling and basically cancel it. So those are the three options there. Usually you can just minimize this window and just keep it running in the background, and you can check up on it and see when your compilations finish. And if you want any more details on this particular window and different options within it, just go ahead and click the help button, and that'll bring you a nice help file with detailed information. So in the compilation status window, there is something called the configuration report. So let's talk about that. In the configuration report, you'll see different pieces of project information. So for example, you'll have the name of the project, the name of your target, and also the top level VI name. It'll also tell you what the start time of the compilation was, in case you want to keep track of that, and some other things as well. So essentially it'll give you the Xilinx compiler configuration for the FPGA VI. Another report that's available in the compilation status window is the device utilization report. So there's actually two times that this report will show up, And one is generated at pre-synthesis, and the other one is generated at the synthesis stage of compilation. And what this will tell you is how much of your device is actually being utilized. So for example, what percentage of your FPGA resources need to be utilized in order to implement your FPGA VI. So if we take a look at this window over there, you can see that there is a table here for device utilization, and you'll see use, total, and percent. So if you look at the percentage, and that percentage is something that's very close to 100% or even above 100%, then that's telling you that your FPGA VI is using a lot of the logic on that FPGA, and it's probably going to fail the compilation. So ideally, that percentage that you see there would be something safely below 100%. So another report that we can look at is the timing report. Again, there are two separate versions of this report as well. One is going to be generated at mapping, which is kind of the estimated values, and another one will be shown at the placing and routing, which is going to show you your actual values of timing during compilation. So the thing to look at here is, if you see here, there's a requested column and there's also a maximum column. So the maximum column is showing you the rates, the maximum rates that your code could possibly attain. And then under requested, that's the rate that your code is actually trying to attain. So ideally, the requested column would be something that is less than or equal to the maximum column. Now, if you're trying to request a rate that is higher than the maximum can be, then your compilation is going to fail. Another report that's available is the Xilinx log report. So this is going to include detailed Xilinx log information. And if you're familiar with Xilinx tools, you could possibly use this report to do some debugging yourself. Otherwise, it's there for your reference. And you can also save that to a file. There's also a compile worker window. And this window will show up wherever your compile worker is installed. So by default, that's going to be on the same computer as your compile server and also on the same computer as your LabVIEW development environment. So notice that on the Windows taskbar, there is an icon there. And if you select that icon, it'll show up a window for the LabVIEW FPGA compile worker. And one thing it'll tell you is the server connection status. So it'll tell you, is my compile worker connected to the server right now? If it's not connected to the server, it's not going to be able to compile anything. Another piece of information that is useful is the jobs. So under jobs, it'll tell you which exact compilation it's currently working on. So this is a way of being able to see what your compilation worker is actually doing. So at this point, exercise 3.2 would be a good exercise to do. In exercise 3.2, you basically are able to take an FPGA VI, you're able to run it, and then start that compilation process and see that for yourself. Right now, I'm just going to go ahead and demo what you would see in this exercise. In exercise 3.2, what you're going to do is you're going to take your FPGA VI and you're going to execute it on the FPGA and have it compile, and then you'll be able to look at the compilation process and look at the reports that are associated with it. So first thing we want to do is make sure our FPGA VI here, Simple Math, has been tested, which we've done already. And to compile it and execute it on the FPGA target, we want to make sure that we right-click here, go to Execute VI on, and make sure that it's on FPGA target. So we have that selected. Now what we can do is we can open up our FPGA VI. In this case, it's Simple Math VI. And we're going to run it. So once we click Run, it's going to ask us, okay, well, where do you want to compile it? In this case, we're just going to use our local compile server, which is on the same computer, and click OK. Now it's generating the intermediate files, so it's creating the VHDL files or HDL files, and it's going to send those to our compiler. So now what you're seeing is our compilation status window, and what we're going to do here is we're just going to go ahead and let our compile worker do the compilation. And you can see in the status what step it's in. Over here, we'll see our reports. So if I click on it right now, you'll notice that it's done the pre-synthesis part already, so I can look at these reports as they're generated. And then at any point, you can also go to the Xilinx log just to get an idea of what's going on. And if you are familiar with Xilinx tools, the text there should make sense to you. So for now, what I'm just going to do is I'm going to sit here and we're going to wait until the compile to finish, and then we're going to look at the reports that are associated with each stage of it. Okay, now it looks like our compilation completed successfully. So it launched our FPGA VI. In this case, it was simple math, and it ran it right away. So this VI, it's not running in a loop, so it basically just does some calculations and spits out the answers. So just to show you, let me try changing some of the values. So I'm going to change X to 2 and Y to 3, and then I'm going to hit run. So when I hit run, this is actually going to be sending it to the FPGA, and this code that we've developed for simple math is actually executing on our FPGA hardware. So let's hit run. Notice it said preparing for interactive execution. So it's taking these values from my host computer, sending it down to the FPGA, and the FPGA was able to send back these values. So notice that X plus Y, 5, X minus Y, -1, X times Y is 6. So looks like our logic is correct. Okay, so let me minimize this VI and let's take a look at our compilation report. Okay, so notice that the status is complete. Right now, we're looking at the configuration report. So here in the configuration report, we have available right away at the beginning of our compilation. It tells us, our project. It's telling us the build specification. It's also showing our top-level VI, simple math, things like that. Okay. So if we go to the reports, let's go ahead and jump to summary first. So summary is what's going to show up at the very end, and it's going to give us a summary of our compilation. So it's going to tell us that our compilation completed successfully. Notice that's going to give us our device utilization. So this is going to tell us what percentage of the FPGA resources we used in our compile. So notice that here is 2.6%, 4.0%, 2.5% of these particular elements. So it looks like this didn't take up very much space on our FPGA. Let's see, and we have timing also. So it's going to tell us whether we were able to achieve the timing requested by our VI. And it's also going to give us our compilation time. So in this case, this VI took about 5 minutes to compile. And it tells us how long each section or each stage of that compilation process took. Okay, so let's go through the different reports. So these reports will be available to you as the stages of the compilation process complete. So when pre-synthesis is done, this will show up and you'll be able to look at it. When synthesis is done, you'll be able to take a look at this report. When mapping is done, you'll be able to look at these two reports. And when the place and routing is done, you'll be able to look at this report. Okay, so these will become available to you as the stage is complete. In this case, we've already finished the whole compile process, so we can look at any of these reports. So let's go to estimated device utilization pre-synthesis. So over here, we see a report of our device utilization after it's doing its pre-synthesis. So it's kind of an estimate of how many resources or how many FPGA resources this VI is going to take. So notice that we're using some slice registers and slice LUTs. In this case, we use this many, and out of this total that's available on our FPGA. So we're only using 4% and 4.5%. Okay. Let's go to the next one. And here we have device utilization after the synthesis stage. So this one will be a little bit more accurate and closer to our final percentage. So notice over here we got 2.9 and 4.2. So usually on these, what you want to look at is the percentage. If the percentage is really close to 100%, if it's like 100% or greater, then that's telling us our compilation might fail because there might not be enough resources on our FPGA to implement your logic. One thing I want to say about the percentage though is the percentage doesn't necessarily, so if the percentage is at 50%, it doesn't necessarily mean that that what you have, if you double it, it's going to reach all the way to 100%. The way that the Xilinx compiler works is as it gets closer to full, so as it gets closer to maybe 90% and higher percentages, it'll start working hard to make things more optimized. So when it's going along at first and it sees that it has plenty of space, it's not gonna work as hard to make everything totally optimized on the FPGA, just because that way we save time and we don't have to have a really long compile just to optimize something when it's gonna fit anyways. So just wanted to let you be aware of that. So let's go to final device utilization after mapping. So after the mapping stage, we're going to see what our final utilization is. So notice that we've got 2.6 here, 4.0, and 2.5. So it looks like in the final utilization, it used another element here, which is a multiplier to make things a little bit better. Let's take a look at our estimated timing. So after the mapping stage, we see that these are different elements or components of our FPGA VI, and these components are requesting these speeds, and it looks like our maximum over here is greater than what we requested, which is a good thing. So if you want to take a look at the requested column here and make sure it's less than the theoretical maximum that that component can run at. So it looks like we're safe here. Everything here is less than the maximum that's associated with it, so the compile should have no problem completing. So that's going to be our estimated one. After the placing and routing stage, we can look at our final timing, and it looks like in the final timing, our requested is still less than our maximum, so it looks like we're good to go. And then here the Xilinx log. If you're familiar with Xilinx tools, you can kind of go through this log, and this will update as your compile is happening, and you can kind of see exactly what the Xilinx compiler is doing. Okay. And I'll just go back to the summary page, and you'll notice on the summary page we have that summary of pretty much everything that happened. Okay, so let me close this. And notice that we were able to run our simple math VI on our compact Rio, and we've got the IP address there where it was where compact Rio was on the network for the IP. And notice that it automatically generated a build specification. The other thing I wanted to show you real quick before we're done is I'm going to the folder where this where my project was. So when I first opened the project, there was no FPGA bit file subfolder. When I compiled this and it finished compiling, remember in the compilation stage, what happens at the end is it generates a bit file that describes how to configure the FPGA circuit to implement your logic. So if we go inside the FPGA bit files folder, notice that we've got a file called something.lvbitx. So the lvbitx file extension is what represents a LabVIEW FPGA bit file. So this bit file is going to be sent to our FPGA, and that's how our FPGA knows how to configure itself to implement your logic. Okay, let's go through some discussion questions. So what is the benefit of having reports generated at different points of the compilation? So what's the benefit of having, the estimated utilization show up first, and then the final device utilization, and then the estimated timing and things like that? Well, one of the main benefits of having reports generated at different points is you can early on kind of see if your compilation might fail. So for example, if you're able to look at the device utilization, the estimated device utilization very early on, and it's something very high, it's something way greater than 100%, well, in that case, you might want to just cancel that compilation because there's a high chance that it'll fail, and then you can go back to your FPGA VI and try to modify it and make it more optimized and use less resources, and then start up that compile again, instead of going through that whole entire compilation process just to see it fail. Let's look at the next one. What if you had not tested on the development computer and the VI did not function as intended? So this is something you definitely want to think about now before you start developing. If you think about it, if I create an FPGA VI and then I didn't check whether the behavior was correct, and I just went and compiled it, maybe it takes an hour to compile. Well, after an hour and it finished compiling and I run it, and then I see that I made a mistake in my programming and I didn't have the right logic, well, I basically wasted that entire hour of compiling when I could have caught that much earlier. Now, if I had tested that VI on the development computer first and hit run, I would have noticed right away that the behavior was incorrect. And I could have just used my debugging tools and corrected it within minutes, right? And then once I know that everything is correct and the behavior is what I intended it to be, then I can go ahead and compile it. And then after, that hour compile or however long it takes, then now I'm just troubleshooting whether it fit on the FPGA. Okay, let's look at the last question. What if your compile fails? Well, if your compile fails, well, this is a good launching point for the next couple of slides and also some of the things that we talk about in the next lessons. What could cause a compile to fail? Well, one, there might not be enough FPGA resources to implement what you're doing, so you might have to optimize that. Or maybe it's not going to meet your timing requirements, and there's ways to help fix that. So we'll talk about that for the rest of the course. Now you can describe the various stages of the compilation process. Next, we will describe various considerations when compiling an FPGA VI.